So what I'm going to talk about today is something called divergence. It really explains why transitional elements have the unique oxidation numbers they have, especially why all of them are +2. Before I get going, I have to review some very important concepts that we've been discussing in class and how it relates to this. First and foremost, we now know the Bohr model was limited for many reasons, but really he had a one proton system and he had a one electron system. And he had these energy levels and this planetary model of his solely based on n alone. N is the quantum number that indexes size. And as I keep saying in class, it's based on proximity. Electrons that that are farther away from the nucleus feel the nucleus less. So his energy levels, or his stability, that's what we're going to talk more about, his stability is based on just distance alone, or n alone. Now we've learned that the stability of an electron, electrons closer to the nucleus are more stable, which means their ionization energies are higher. We've talked about this. Ionization energies gives us a window into the atom's ability to hold on to electrons or be stable. Now, electrons existing farther away in his atom were unstable because of the proximity issue. You're away from the nucleus. It's the inverse square law. Coulomb's law was the ionization energy of the electron in the first energy level over n squared. It's an inverse law. So as we jump to the n equals 2, you divide by 4, and this electron feels a nucleus as fourth as much, meaning it's as fourth as stable. Okay, meaning it's 4 times more unstable, if you want to think of it that way. But its ionization energy is less. Now, of course, we now know that this was all dependent upon n number, the Bohr model. Now, we now know when you add another proton into the mix from our study, now we're changing the Z number. And I want you to use Z. Z is for nuclear charge. And when you increase the Z, okay, and put another what? Proton in here, things aren't as simple, because now the difference between a one proton system and two proton system for the same number of electrons, we use the Z squared rule, right? So if I have an isoelectric series, like for instance, if I have hydrogen and I have helium plus, that's helium losing an electron. They both have the same number of electrons. But the helium plus, because it's atomic number 2, and 2 times the number of protons, its Z is doubled, the Z square rule comes into effect, and we can now measure that Z, so 2 squared, it's going to be 4 times more stable in the same orbital, because there's double the protons. So Bohr's model falls apart with another proton being added, because what happens is now these shells start moving, okay, toward the nucleus. And what we're going to learn today, they don't all move the same amount. That's what divergence is about. Now, of course, the Bohr model fell apart even more because, well, because when you start adding another electron into the scheme, now you have electron-electron interactions or repulsions. And if you have electrons repelling themselves, we now have something called ZEF, which is Z effective nuclear charge. This is what the electron actually feels. Meaning, if there's an electron in its way toward the nucleus, here's the nucleus, and this nucleus is trying to pull on or attract this electron coulomically, this electron here is shielding or screening it because of the repulsive force. Now, I guess I should draw that arrow the other way, because what you're going to have is this electron is going to be drawn into the atom or attracted to the positive charge, but this electron here is going to repel it. And by the repulsive forces, this electron feels the nucleus less. So its effective nuclear charge is going to be less than the number of protons. So if you've got 2 protons, like in the case of helium, okay, and in regular helium you have 2 electrons. Well, that one electron is going to repel the other and shield it, so the other electron feels the nucleus less. And its effective nuclear charge is not going to be 2, it's going to be less than 2 because of that repulsion. So when you add another electron into the mayhem here, that also changes all the energy levels. So that every single electron has a unique set of 4 quantum numbers, as we've studied. And the reasoning is because each electron has a unique set of energy levels, quantized energy levels, based on number 1, the n, the size of the orbital, 2, the number of protons, the nuclear charge, and what that electron actually feels, Z effective nuclear charge or effective nuclear charge, due to the shielding. See, the Bohr model only took into consideration the n, and that's why it was limited in scope. All right. Now, what am I getting after today? Well, I'm getting after today this idea of um, divergence. Before I do so, there was a couple of questions on last night's homework that I want to definitely go over here in terms of the electron density, okay, plots of these orbitals. First and foremost, because it was a one electron system, um, Bohr did not have any sublevels. He didn't have an S, a P, or a D. The azimuthal or the L number, the quantum number. That only arises when you have other electrons. This creates the orbitals. This fine-tunes the atom, okay? And we'll talk about that. But getting back to this, you know, there's sometimes you see drawings like this. This is a circle that represents a 1s orbital. And you learn that the 2s is also spherical because it has a 0 for the L letter or quantum number, meaning it has 0 preferred axes. It's a circle. And this is a 2s. And the 2s encapsulates the 1s. And of course, the 3s does so also. But these aren't great indicators, and you'll see these drawings all over the place. These aren't great ways to think about them. Yes, this line represents the most probable location of finding that wave or electron, but it doesn't show the interpenetration. So let me just show you what happens here. Okay, let's say I have a plot. Okay, we're going to do a graph here, and it's going to show electron densities. And let me show you 1. This would be 1s. All right, and 1s has no nodes, so the electron density. Now, if you look at the most probable location of that wave is right here, and that's what this represents, this circle. That circle represents that location, but you can have some outside. It's like tunneling electrons. They're going a little farther than the maximum location. But this is probability, right? Okay, we're doing quantum mechanics. Waves. Now, 2s, a little different. The 2s, whoa, has some penetration here and then goes up. Now, it's a little lower because this was the entire density of 2 electrons. This is still 2 electrons being stretched out. So this is the 2s. But look at that. The 2s has some what? Has some electron density in the same region as the 1s. So the 2s electrons, we always say, well, the 2s are way outside the 1s. Not really. They penetrate. There is some electron density in the 1s, which means there is some electron what? Repulsions going on that make the 2s be more unstable. The reason why 2s is more unstable is because of these electrons, these other electrons creating effective nuclear charge that's lower, right? Now the 3s, let's go red. The 3s has 1, 2, 3 lobes. Now I'm getting lower because I'm stretching the 3s over a long period. Let's do a 4s. Same idea. 1, 2, 3, and 4. Okay, I'm stretching out the density. It's the 4s. So the reason that the 2 and 3 and 4s, okay, are essentially less stable, yes, there's a proximity issue, but what creates the proximity issue? Probably, and who knows, these effective nuclear charge differences due to the repulsions of electrons. There is, look at this is the 4s. Look at this. It's getting in the way. It's repelling these. Okay, but this represents all the density of where the 4s electrons can be. Remember, they're not point charges, they're waves, they're standing waves. Now, interesting enough, you guys have learned that this is the s block. All right? You've learned this is 1s, 2, 2s1. Okay, sodium is 1s2, 2s2, 2p6, 3s1. Right? These are all s block. Now you notice that calcium, okay, is 1s2, and it's 2s2, 2p6, 3s2, 3p6, 4s2. Okay, and then scandium is the same thing, but now you're starting to fill in the D subblock. Now, let's write the calcium in terms of a little condensed version. Let's do argon, okay, and then we have 4s2. Now, you know in the third integer level, you have 3 sublevels. How do I know that? From my quantum numbers. When n equals 3, right, what's my L number have to be? Well, it goes from n, which is 3, to n minus 1. All right, so L is equal to is 2. L is equal to m sub L is equal to so the L number, okay, is going to be, if you remember, if n equals 3, there's 3 orbitals because n is equal to the 0 to n minus 1 rule. So we have 0, right, to n minus 1. Well, n minus 1 is 2. So we have 0, 2, 2, which means you have 0, 1, 2, and 3. These are the L number, well, I'm sorry, 1 and 2. 0 means the S, 1 is the P, and we have a D. My friends, in chemistry, we have 3 orbitals that belong to the third principal energy level based on our quantum numbers. Okay, so if that's the case, how come we fill the 4s before the 3d? Right? Why shouldn't this 3d be up somewhere? We have 3p6. Shouldn't you have 3d? No, the 4s fills first, and the reason is, let's draw the 3d. The 3d is somewhere here. Oops, not that. Somewhere right here, and it's pretty high. It's got a lot of density because it's going to hold 10 electrons. So this is the 3d. Now you say, whoa, the 3d looks like it's closer to the nucleus. Remember, the nucleus is over here, and this is the density closest. But wait a minute, the 4s has a lot of what? Density closer to the nucleus than the 3d. So electrons will fill the 4s first. That's why potassium is 4s1 and calcium is 4s2, but scandium would be argon, bracket, 4s2, 3d1. Now we're going to fill the D's because we fill that. You say, okay, I knew that, but now it makes more sense because of these other penetration of the what? The 4s closer to the nucleus. Okay, now the 3d doesn't have any nodes, it just starts there. That kind of makes some sense. Now what doesn't make sense for a lot of students is, why do most of these elements become +2? Why do these transitional elements all become +2? And some people memorize, well, they lose from the s first. Now, why would you lose from the s first if you fill the s first? The Aufbau principle states electrons fill earlier orbitals first, so that makes sense. But why would I lose them? Should I lose them from the d? They seem to be farther away, okay, on average. Well, here's what happens, and this is so cool, all right? As we start adding, okay, as we start adding electrons, this would be 3d1, 3d2, 3d3, this starts to pick up some density, right? Some electrons are filling that. Now these electrons, this density starts shielding for some of the 4s electrons in this area. So that starts to happen, but that's not everything. The most important part is this. What did I say earlier on? As the Z number increases, the orbitals get pulled in, but they don't all get pulled in the same amount. So watch what happens. As I go from scandium, who has 21 protons, and titanium, who has 22, and vanadium, who has 23, what happens is the stronger Z, the higher Coulombic attraction, starts pulling these orbitals all to the left, but not equally. Think with me for a second. Who has a lot more denser amount of electrons? And I always use electron density. Who's got a thicker amount of negative charge? This area of 3D or this area of 4s? Now remember, 4s only has 2 electrons. And it's stretched out over a large area. So its charge density is very low. This 3D, once you start getting around this area where you have 5 and 6 and 7D electrons, I'm not sure exactly where it starts, but right around here, here's what happens. Once you start adding enough electrons in this area and making this dense enough, and at the same time have a high enough Z or nuclear charge, you will pull, okay, you will actually pull the 3D, this is the cool part, closer to the nucleus than the 4s. The 4s gets pulled too, but not nearly. So this 3D starts to move. Let's pretend it happens right here. It moves over here now. If the 3D is now over here, clearly the 3D, now you say, well, why would it move? Clearly, it has a higher charge density. This thick amount of electrons, remember there's 10 electrons that can be held in this little area, is going to be attracted to the nucleus more as it gets stronger than the 2 electrons stretched over a large area. Because the charge density, which means more negative charge in a small area, it's going to attract the nucleus more. So this moves closer to the nucleus than the 4s, and we call that divergence. And because there is divergence, okay, not spelled very well, or at least written very well, because of the divergence, then the 3D becomes more stable, and filling the 3D becomes a priority of these elements. Remember copper, and this is the kicker, we did this a couple weeks ago, we didn't know why. Copper, okay, is 3D9. You might write this, you might say, okay, argon, 4s2, 3d9. If you write that, I tell you it's wrong. You need to know it's going to be 4s1, 3d10. Why? Well, it was in the s, but when this moves in closer because of more electrons attracted to the positive nucleus, electrons that are in the s that are remaining, okay, if there's 9 here, don't electrons want to go to a lower energy orbital first by the Aufbau principle? Yes. So one of these electrons will jump to the D because now the D is lower in energy. And some people will write their configurations and switch them. Some people will write copper as argon 3D10 4s1 to show that. Okay? So that's why we write it 4s1 3d10, because you know right around here the 3d moves in closer because the nuclear charge is great enough to attract the more dense region, because you have a lot of D's now. It doesn't happen earlier on because the nuclear charge isn't great enough to make it move, and there's not enough electrons being added to the D. It's so cool. Now, why do they all become +2? Easy, guys. All of these transitionals love to become +2 for the most part because you're exposing 2 electrons. Electrons are going to be lost in the orbital that is less stable and farther away. Notice copper can become +1. Notice silver can become +1 for the same reason. Why can copper or silver or gold become +1? Because they've got 1 electron in the outermost energy level that's the most unstable. It makes sense. All right, so this is what I did today for those that missed.